Every drop of clean water we use has an energy footprint. From extraction and treatment to pressurization and distribution, water is one of the most energy-dependent services in modern cities. When electricity stops, pumps shut down, treatment plants slow, storage tanks empty. Water supply is no longer just a hydraulic system. It is an energy-driven infrastructure. Designing a self-sufficient home water system, therefore, begins with a fundamental question: how much energy does water production actually require, and how can we provide it sustainably? In centralized systems, water often travels hundreds of kilometers before reaching the user. It is pumped across elevations, treated through multiple processes, and maintained under constant pressure inside distribution networks. Each of these steps consumes energy. In some regions, water supply is among the largest single consumers of electricity. This means that the water coming out of a household tap already carries a hidden energy cost, paid through utility bills and environmental impact. Decentralized production changes this relationship by shifting energy use from the city scale to the building scale. Atmospheric water generators rely on controlled cooling to reach the dew point and produce condensation. This process requires electrical energy, primarily for air movement, compressor operation, and thermal exchange. The exact demand depends on humidity, air temperature, and system efficiency. In optimized conditions, modern systems can produce drinking water with energy intensities comparable to desalination. But unlike desalination, this production happens exactly where the water is consumed. There are no long-distance transmission losses. The key to sustainability is not reducing energy use to zero, but matching production with renewable generation. Rooftop solar transforms the building into a micro-utility. During peak sunlight hours, surplus electricity can be used to produce drinking water, recharge storage systems, and power treatment processes. This creates a direct conversion of sunlight into water security. This ensures both efficiency and reliability. Water becomes a managed output of the home's energy ecosystem. In dense urban environments, complete energy independence may not always be feasible. Hybrid systems provide a resilient alternative. Renewable generation covers the primary demand. The grid acts as a backup. Waste heat from air conditioning systems pre-cools incoming air, improving water production efficiency. This multi-layered approach reduces operating costs and maintains continuous supply even under variable conditions. Water production does not need to be constant. By analyzing weather forecasts, humidity patterns, and household consumption, smart systems can schedule operation at the most efficient moments. For example, producing water during periods of high humidity, using excess solar energy at midday, reducing operation during peak electricity times. This transforms the system from a passive machine into an adaptive infrastructure. Efficiency is no longer static, it becomes dynamic. When water and energy systems are designed together, the result is more than independence. It is synergy. A net-zero water energy building produces its own drinking water, powers its treatment processes with renewable energy, and minimizes external demand. This is not only an environmental achievement, it is a new model for urban resilience, where buildings actively reduce pressure on public infrastructure. In the next generation of sustainable housing, energy does not just power our homes, it secures our water,